Test. Good afternoon. So my name is Charles Masson. I am a data scientist at Datadog, and today I'll be focusing on statistical distances and more specifically how we can use statistical distances to detect anomalies. So last year at Datadog, as we were designing an anomaly detection algorithm, we started experimenting with statistical distances. And as some of them are not implemented in common Python libraries or projects, we decided to implement them and to contribute them to SciPy. So I explain how and why we considered and use statistical distances to detect anomalies. So let me start by saying a few words about Datadog to give you a bit of context here. So Datadog is a SaaS-based infrastructure and monitoring platform. So basically, customers can send time series data, metrics, application traces, and logs. We process everything, and customers can visualize all of this in dashboards, such as the one you can see on the right here. This is about trillions of data points that are processed every day, and we also have alerting features, such as algorithmic alerting features, anomaly and outlier detection, and predictive alerting, which is about notifying the customer before something goes happen in their infrastructure. So as I mentioned, customers send application traces, which means that, for example, if they have a web application, they can send application traces for the web request, which means that we know how much time is spent processing each operation when processing the web request. So we know the duration of the full web request. And so what you can do here is that you can look at time buckets and look at all the web requests that happen during a bucket. You look at the duration of those web requests, and then you look at the percentile. So here we look at the 50th, 75th, 90th, and 95th percentiles of those web request duration, and you can plot that over time. So this gives you this kind of graph. You can also look at a specific time frame and look at the requests in this time frame, look at the distribution of the latency of those requests. So you can get this kind of histograms, and we also have markers for the percentiles here. So now when you see this, you might ask yourself, is this distribution the expected one, the usual one, or is this distribution anomalous in some way? So we can imagine that we have a baseline of the distribution that we expect. We can build this baseline based on a time frame during which we know the web application worked smoothly. And then we look at the distribution over the last minute, and here it's clear that the values are shifted towards the larger values. We can see that the percentiles are larger, so we can probably flag this distribution as anomalous. So this is a qualitative qualitative criterion, but we need a quantitative way of doing that. We need an algorithmic way of saying that this distribution is anomalous. So the first thing that we can do, the most obvious one, is looking at the sample statistics. So let's say we have our baseline distribution B and the test distribution T. We can look at the averages. And in this case, because we have a significant difference, we can say that the test distribution is anomalous. However, this won't work in all cases. So in this case, the test distribution has a longer tail. So there is a significant amount of web requests for which the duration is more than what it should be. But if we look at the averages here, we won't see a significant difference. So the average is not able to detect exhaustively all the anomalies. What we can imagine doing here is looking at the maximum, but if we look at the maximum, it will probably be sensitive to one single request that for some reason might have timed out, or maybe there was a network issue at some point, and the maximum duration won't reflect the overall behavior. So the maximum is not the right thing to look at, but we can still look at, for example, the 90th or the 95th percentile. In this case, if we look at the 95th percentile, we do see the difference. So we can flag the test distribution as anomalous in this case. But you probably imagine what the next slide is. We can still imagine cases where the test distribution is obviously abnormal, but the 95th percentile doesn't say anything. So once again, the 95th percentile can't catch exhaustively all the anomalies. So at this point, it's clear that using a single sample statistic is not enough. What we can do is using multiple sample statistics. Maybe we can use the averages, some percentiles, the standard deviation, look at how different they are. But then we need to make sure we have a good criterion to aggregate all those results and say when it should be anomalous or not. So this would probably involve some tuning. The other way is using statistical distances. So in short, statistical distances are distances between statistical objects, samples, distributions. And a way to introduce statistical distances is starting with something that's commonly known in statistics, which is the Kolmogorov-Smirnov test. So this is a statistical test that is commonly used to say whether a given sample is drawn from a reference distribution or whether two samples are drawn from the same reference distributions. So we can consider the latter case here. And the way how this test works is that you look at the cumulative distribution functions of both empirical distributions that we have here, and you look at the maximum absolute difference between the cumulative distribution functions. This gives you a number between 0 and 1. And now what you do with that number is that you would have what we call the null hypothesis, which is that both samples are drawn from the same distribution. We have a critical value at significance alpha, which depends on how confident you want to be on the test. Usually those values are tabulated, but you can also compute them from the Kolmogorov distribution. Yeah, sorry. Better. Yeah. And what you would do now is, based on the value that we computed in the previous slide, which is between 0 and 1, if that value is less than the critical value, we accept H0. We consider that both samples are drawn from the same reference distribution. Otherwise, we reject H0. So we can use this test as it is as a way to say whether or not our test distribution should be anomalous. Basically, we consider that if we reject H0, this is a criterion for saying that the test distribution is anomalous. However, this only answers a yes or no question. We don't have we don't know to what extent the distribution is anomalous, and sometimes we might want to maybe to pinpoint the most anomalous distribution when we have multiple distributions. So we need a quantitative measure of the anomalousness. And when we look at that, we can clearly do it very easily by keeping the KS value here, which is the value between 0 and 1. And the great thing about that is that it gives a distance between distributions. So if you have three distributions x, y, and z, KS verifies that it is non-negative. It is 0 if and only if both distributions are the same. It is symmetric, obviously. And we have the triangle inequality. So the great thing about that is that now you can forget about the distributions. You can just consider that there are points in a metric space, and you can apply all kinds of algorithms, outlier detection algorithm, clustering algorithms, that would work in any metric space. So if you notice that your points, which are your distributions here, are all close together, but one is far away from the rest, you can probably flag that one as an anomaly. So we have a metric space, so this is great, but we still need to make sure that the distance is powerful enough so that we can detect all the anomalies. And a way to know how this distance works is to look at some examples. So we can start with uniform distributions. So we have two uniform distributions that are shifted from each other. If we plot the cumulative distribution functions here, this is what we get. Now we can imagine that we shift one uniform distribution with respect to the other with a shift alpha, and we can look at how the distance increases when we increase alpha. And we can see that it increases linearly until we reach 1, and then it plateaus at 1, which makes sense because the distance, the value is always between 0 and 1 for the Kolmogorov-Smirnov distance. But it's not great because that means that when the distributions are close, we can say how close they are, but when they are far away, it's always 1, so we cannot say how far away they are from each other. So you might imagine that this case is artificial. In practice, we don't have uniform distributions, but we might have things that look like that. So here we have three distributions, the baseline B, the test distribution T, which has a bump on the right, and the T prime, which also has a bump but further away. What we'd like to see here is that T prime is further away from B than T is. But if we look at the Kolmogorov-Smirnov distances here, they are about the same because this maximum absolute difference between the cumulative distribution functions are the same. So in practice, we might not be able to say that T prime is more anomalous than T in this case. So we need another notion of distance that somehow account for the fact that T prime requires more work to make it match B than T. And this is actually the idea between the Earth movers distance. So let's imagine that our two distributions here are heaps of Earth, and that our job is to move the blue distribution to make it match the purple distribution. So we're going to take each part of Earth in the blue distribution and bring it to an area in the purple distribution. So this way we define a mapping, which we can call gamma. Gamma of x and y is the amount of Earth that we move from x to y, and the conditions on the right here translate the fact that we start with the B distribution and we end with the T distribution. We can consider all such possible mappings, and for each mapping we can consider the work that is involved, that we define here as the amount of Earth that we move times the distance over which we moved this amount of Earth, and we sum obviously over everything. Now, if we consider the mapping that is the most efficient, that is to say the mapping that requires the least work, we define the Earth movers distance. So the Earth movers distance, in other words, is the minimum amount of work that is involved in moving the blue distribution to the purple distribution, where work is amount of Earth that you move times the distance over which you move it. And this is also known as the first Wasserstein distance. So let's look at what this distance looks like on our uniform distribution. So now, as we increase the shift, we keep increasing linearly even beyond 1. So this is better than the Kolmogorov-Smirnov distance in our use case. However, there is something that seems bad with the Earth movers distance, is that it is defined as an infimum. So we could imagine that it's going to be computationally expensive to calculate. However, in the one-dimensional case, there is another way to express the Earth movers distance, which is using the cumulative distribution functions again. So here we have two distributions. We can look at their cumulative distribution functions. And if you look at the area between the cumulative distribution functions, we can prove that this is equal to the Earth movers distance. So this gives us a very efficient way to compute the Earth movers distance, much more efficient than computing the infimum. This also gives us an intuitive way of understanding what the Earth movers distance is. So basically, now if you see two distributions, you can imagine their cumulative distribution functions and have an idea of what the Earth movers distance looks like. So on the bottom graph here, if you swap the axis, you won't change the area, but you will get the quantile functions instead of the cumulative distribution functions. So that means that we have another way to express the Earth movers distance, which is basically by the area between the quantile functions. So now that we know that, we can go back to those distributions and look at what the distance looks like. So basically, we look at the area between the cumulative distribution functions, and now it's clear that on the right, the distance will be larger than on the left. However, we can still imagine some cases for which we cannot see anything using the Earth-Mover's distance. So, for example, here we have on the left two uniform distributions, B and T, and on the right we have T prime that we generate by accumulating mass in a single point. We'd like to say that T prime is further away from B, but if we look at the Earth-Mover's distance in both cases, which is the area between the cumulative distribution functions, by doing a bit of geometry, it's clear that the distance is almost the same in both cases. So the Earth-Mover's distance is not affected by this local deformation. However, what we can do is work in from the Earth-Mover's distance. So we saw that the Earth-Mover's distance, which is also known as the first Wasserstein distance, is this infimum, which we can write as the area between the quantiles. If you look at the top line here, if instead of taking the absolute difference between x and y, we take the absolute difference to the power p, so that we penalize more when the distance, the absolute difference is larger, we can define another family of distance. So basically, this is what we do here, and we take the whole thing to the power 1 over p to make it a distance. So we define a new family of distance, which is all the Wasserstein distance. And yeah, basically the pth Wasserstein distance is defined as this. And if p is larger than 1, we will be able to catch the local deformation in the previous example. And the great thing is that we can prove that we can still compute this from the quantile functions. So this is, we can easily compute it this way as this integral. So if we look at the bottom line here, we are basically looking at the expression with the quantile functions and taking this to the power p. What if we do the same with the cumulative distribution function? So in other words, what if we take this expression of the Earth-Mover's distance and we take the absolute difference between the cumulative distribution functions to the power p? Actually, when we do that, we define another family of distances, which is this. And if we take p is equal to 2, this is a particular case, and this is the Kramer-von Mises distance, also called the Kramer distance, and this is related to the Kramer-von Mises statistical test. So if we look at the Kramer distance on our uniform distributions with the shift, basically it will increase as a square root function. So now that we have the theoretical background behind those statistical distances, we need to implement them. And what we need to do is computing distances between practical data between actual data, so between data samples, histograms, or empirical distributions. And in our case, we're just interested in the one-dimensional space case. And we can actually encode all those objects with values and weights. So if you have data samples, you have values, and you can use weight as the number of occurrences for each value. If you have histograms, the bin locations are the values, and the bin heights are the weights. And you can do the same for empirical distributions. So this is the way how we implemented those statistical distances. So we opened a PR last summer in SciPy, and so we implemented the first Wasserstein distance and the Kramer-von Mises distance. The Kolmogorov-Smirnov distance is already implemented in SciPy, and our PR got merged last August. So now you can basically import that Wasserstein distance function. Here we generate two samples from a uniform distribution and from a normal distribution. You can compute the Wasserstein distance in this case. And if you have weights, so let's say if you work with histograms, you can also do it this way. So this is one particular use case of statistical distances, but we can do much more with statistical distances. So the first thing is that statistical distances, for some of them, can be defined in multidimensional spaces and even in metric spaces. This has applications in pattern recognition and image processing. So for example, if you work in the two-dimensional space case, you can define the Earth-Mover's distance in a two-dimensional space, and you can use that to say how close two images are. There is also a weaker notion of distance, which is the divergence. So the divergence only verifies the non-negativity and the identity of indecisibles. And one specific case is the Kullback-Leibler divergence. So basically, this is defined as this. So we use the lowercase p and lowercase q, which are the densities of p and q. We can also see that this is not symmetric. And the thing is that you might have used this Kullback-Leibler divergence without realizing, because we can show that the maximum likelihood estimation problem is actually equivalent to minimizing the Kullback-Leibler divergence. So when we see that, we might ask ourselves, why would we minimize this particular divergence? Why wouldn't we try another divergence, or why wouldn't we try to minimize a statistical distance? What would that change? And the point is that if you look at the expression of the Kullback-Leibler divergence, you can see that we look at the densities at single points. We look, roughly speaking, at the ratio between them, and then we sum over everything, which means that if you have distributions with high density areas that are not exactly at the same place, but a bit shifted away from each other, you cannot detect that with the Kullback-Leibler divergence. You cannot see that there are high densities areas that are close if they are not exactly at the same place. And that's actually one issue that we saw lately with generative adversarial networks. I won't go too much into details here, but basically generative adversarial networks are machine learning models that are intended to generate data that looks real or that looks like some reference data. So this kind of networks first appeared in 2014. And at the time, the loss function that was used is the Jensen-Shannon divergence, which is a symmetrized version of the Kullback-Leibler divergence. And a few years later, in 2017, we saw the Wasserstein generative adversarial networks, which, as you can imagine, use the Wasserstein distance as the loss function. And the reason for doing that is exactly what at least for part of it, what I described in the previous slide, which is the fact that if you have distribution of data with high density areas that are not exactly at the same place, basically with modes that are a bit shifted from one another, you cannot detect that with the Jensen-Shannon divergence, but you can with the Wasserstein distance. And the same year, in 2017, we also saw the Cramer generative adversarial networks. So those ones use the Cramer distance as a loss function, and it actually solves a few issues that we might have with the Wasserstein generative adversarial networks, especially when we work with samples where we might have bias. So this ends my talk. So if you're interested in these topics, we wrote a blog post. You can see the link here. So there are references and also an animation so that you can generate distributions and try statistical distances for yourself. If you have questions or feedback, you can reach out to me, or you can ask questions now, I guess. And if you're interested, we're also hiring. Thank you.
Thank you for your talk. Are multidimensional distances are implemented in SciPy in your PR, or is it just only for one-dimensional PDF and CDFs?
It's only the one-dimensional case. I think for the Earth Movers distance, there is one library which is called PyEMD, which would work in any case because basically you specify the distance matrix. However, in the general case, you cannot do the optimization that you do in the one-dimensional case, where you just look at the area between the cumulative distribution functions.
So to generalize this distance from area to volume or some multidimensional area, I have to write it down by myself.
So actually, this equivalence between the Earth Movers distance in the one-dimensional case and the area between the cumulative distribution functions, this is really specific to the one-dimensional case. And I don't think there is such equivalence in the more general case. So I don't think there is such thing as a volume that you could compute in a 2 or 3 dimensional case, and that you could look at to compute the Earth Movers distance. I don't think that's possible.
Well, Kolmogorov-Smirnov distance is really easy to generalize that way. Why it's not the other way from Mother Earths and other distances you were talking about? Anyway, thank you. I think we're gonna talk later.
Thank you.
Hey, thank you. Yeah, I mean the Waters mover distance. It's not really Just broken or something? Okay. The outermost vertical distance isn't really equivalent to the. I'll just talk like this. Is that okay? No? Okay. It's not really equivalent to the integral, right? Simply because it's the absolute distance between the curves. Yeah?
The Earth-Mars distance?
Yeah, the Earth-Mars distance, sorry, yeah.
This is the area? Between,
Yes, exactly.
Yeah.
It's the area, but it's the absolute area. So it doesn't really matter how it's signed, right? So if the curves cross.
Yes, you
Okay.
would take the area in the other way.
Exactly.
But as a
So you would
positive
not
value.
subtract it, you would add it, yeah.
Yes, you
What-
always add any part between the cumulative distribution functions. Yeah.
Okay. What does that say about the robustness to noise? Simply because if you have if you have a lot of noise, simply because with real data the distributions will never look that smooth, you'll basically get these crosses all the time, and you'll get an added area which might correspond to a real area where you actually have different distributions.
So I think in this case we need to look at the noise compared to the scale of the data. So basically, even if you have the thing that you're describing, maybe it's still relatively small to the scale of the data. I think that it depends on the use case once again, but generally speaking, the Earth-Movers distance is much more reliable when you have noise than the Kolmogorov-Smirnov distance, for example, because this is an average somehow, but when you compute this area, this is an average, whereas in the Kolmogorov-Smirnov case, you look at the maximum, so maybe you have some local deformation or some local noise, and this is going to change completely the Kolmogorov-Smirnov distance. So I think, generally speaking, it's quite resilient to noise. Maybe there are some cases that I don't have in mind for which it's still an issue. But yeah, I think it's usually okay with noise.
Okay, thanks.
Sure.
So I just have one remark. Normally, you can link this optimal transport map to the Monge-Ampère equation.
To the what, sorry?
The Monge-Ampère equation. So did you heard about it?
I'm not sure I heard about
Okay.
it.
So it's a way to solve the Monge-Kontorovich problem, because this is what you are doing. And one interesting thing with it is that you can solve it for high-dimensional problems. So basically what you solve is a scalar function, but its a gradient is the map that you are looking for. But it's a completely different way of doing it.
I think I see what you mean. I mean, I've read things about it. I don't know it very deeply, but yeah, I see. I think I see what you're referencing. Yeah.
Okay, if that's all, thank you.
Thank you.
No?
It's getting there. It's getting there. So, 44 megabytes.
Oh.
Who's that?
Somewhere else.
On iCloud maybe? Everything's there, so no computer. Yeah. What's that?
UC drive.
Aber du lädst schon runter? Du lädst schon runter? Nee, das Ding geht. Wir müssen jetzt nur die Aufwand runterladen.
So please go all off your laptops, stop downloading everything so we can transfer the presentation to the other laptop. The sooner we get there, the sooner we can get started. No, it's not working at all. So it shows 1 minute left, but I think we can start without the presentation. These guys will get this fixed. Yeah, they're getting it done with the other laptop. I think we can just start. So my name is Peter Hoffmann. I'm an engineer at Blue Yonder. If you've seen the keynote from this morning from Felix, yeah, we are using data science and machine learning in the retail sector. I mostly work in the backend team. I'm working with Python for, I don't know, more than 10 years. I'm now responsible for infrastructure services at our company, for the SQL databases. So we provide our data scientists with the data so that they can do machine learning. Beside my work at Blue Yonder, I'm also one of the organizers of PyCon.de, which will be held in October in Germany, and also a co-founder of PyData Karlsruhe. So now I would need my presentation.
USB key.
It's going. We are at 30 megabytes, only 10 more to go, so I think we're going somewhere. Yeah, but click on this one. That's okay. Click here. Not just open it. It's okay. Leave it running. Just in case. Okay, play. So, okay, you have seen this. You have also seen this. So I really love to see you all in Karlsruhe in October. So we have already sold more than 300 tickets. So if you really want to go there, hurry up. Lots of cool talks. We will have Wes McKinney as a keynote speaker. We will have tutorials, and we have a sprint on the weekend. So I'd love to see you all there. So what I'm talking today is Apache Parquet as a columnar data storage for large data sets. I'll show a little bit why we use it at our company, a little bit of architecture, why we needed it, and why you could probably benefit in your scientific workflows or also in your machine learning workflows. That's again what we do at Blue Yonder. So we do machine learning in the retail space. Basically, the customer sends us every day lots of data. It might be data like sales, stocks, product data. We do data quality checks on this data, then put it into a SQL database. And then from there, we start our machine learning algorithms. And in the end, we predict the density function with predicted sales or the predicted demand. And we use this to implement replenishment, so to tell our customers how much of each good they need to order for their stores so that they don't go out of stock or have too much waste. So that's what we do as a company, and it's my day-to-day business. We use supervised regression, so we have lots of input features that go into our machine learning pipelines. And for the bigger customers, we have about 500 to 1,000 stores and about 20,000 products. And we have a horizon where we predict about 15 to 30 days. So that's about 20 million decisions per day that we calculate each day for our customers. So that's quite some data. If you look at the data flow, at the moment we store much of our data in an in-memory columnar distributed SQL database. That's a multi-node database. We have data sizes about 10 terabyte. And from there, our data scientists build models, and they can pull the data out of the database. We have a distributed cluster which runs on top of this cluster. We have running Apache Mesos and Aurora. And then we use the normal DAS, Jupyter, Panda stuff to do our machine learning. Once we are done with calculating the predictions, we are inserting them back into the database, and then the customer can pull the predictions or the order proposals to get it into their business processes. What we have seen, there are two things that we don't like. The one thing is the database as a bottleneck. So we can at maximum pull out data with 10 or 15 connections from the database. And we could use our machine learning algorithms, could use trivial parallelization. And we have running up to 500 jobs, and most of them are waiting to get the data out of the database. And even worse, when we want to get the data back into the database, we can only insert with one job at a time. So these are the bottlenecks that we don't like. Another thing is to compare models or model quality. It's always good to have a static data set where you can run different models. But as soon as the customer starts changing the data in our database or via our APIs to the database, the input data changes, and then it's very hard to do model comparison. So we always needed to have a second database where we copy the data to, and this gets quite weird. So we have been looking, okay, how we could improve this workflow, and then we came to Parquet as a data format. So what we have seen in our company, our data scientists, they love Python. It's a really good companion for our data scientists, but it's not been the best tool for getting large amount of data in and out to the Python ecosystem. So why do we care? We have large sets of data in the file system in a non-uniform schema. We want to execute queries against. And most of the time for the machine learning, if you do clustering, you're not interested in the whole data, but only in small subsets of the data. If you look into different ecosystems, mostly in the Hadoop Java world, you have Hive, Pesto, Impala, or Drill. They are a little bit, or they have been a little bit more advanced in this feature. If you are interested more in the topic of deconstructed databases, I can just tell you this talk. It's very good. It really shows how in the Hadoop's ecosystem they went from databases to deconstructed databases with all the different parts: data storage, query execution planner, and then the real query. But that has not been available in Python, so that was pretty bad. What do we know, or what have our data systems normally doing when they want to get data into Python and back out again? I would say use Parquet, but there was no Parquet 2 years ago. So mostly they use CSV, and CSV is not statically typed, and you have all these different date formats and all this stuff. Though this was not really good. So we saw, okay, CSV, that can't be a solution. And then we looked into the ecosystem and we found Parquet. It's already available in the Java ecosystem. And then we saw, okay, there's still some potential to use it in Python too. So what's the benefit of storing data in a columnar fashion? So if you look at a normal table with data that we usually use for predictions, so days, location, products, and the sales number. In the traditional memory buffer layout, you have it row-wise, so you have each entry for one row after another. In a columnar store, you store all the values for one columnar after each other. And this is much more efficient for compression or for doing analytic workflows on the data. So get me the sum of all sales for some predicate, for example. So this is much better storage format, and it's much more suited to get the data into pandas. So what is Apache Parquet? It's a columnar on-disk storage format. It was originally invented or developed by Cloudera and Twitter. It's now a top-level Apache project, and since fall 2016, it has full C++ support, and most of the interfaces are also exposed to Python. And it has been, or it is, the state-of-the-art format for the Hadoop ecosystem. And why do we think, or why does Parquet help us? With the columnar format, you can run vectorized operations. With efficient encoding and compression, you can really use the features from the CPU. You can do predicate pushdown. I'll show you later what it is. And using a library, it's a language-independent format, so it's really the de facto format for all different programming languages and not bound to one programming language. At the moment, there are 2 projects that expose reading Apache Parquet files within Python. So the one is Fast Parquet. It's more from the Dask space, and the other one is the Apache Arrow project. Apache Arrow is a much broader concept that really tries to define a unified memory layout, and then use different or expose it to different programming languages, and on the other side also expose it to different storage technologies. So you have a Parquet reader that maps to Apache Arrow, and then pandas can use the Apache Arrow implementation without writing additional code to just interact with the Parquet files. And on the other hand, there is working on the Kudu software or Cassandra, so that they also expose their results in the Apache Arrow format, and then you can get it into Python without much additional implementation work. Where we could really have benefit for all this machine learning stuff to get the data fast in and fast out. So that's it. Thanks for your attention, and if you have questions.
You mentioned the predicate pushdown for querying row groups, and you mentioned partitions.
Sorry guys, apparently we have some whatever problems with the connection. So I might start as well while we are fighting another laptop without the slides. Or maybe if I could use some, well, I can start without a slide. There is not important in the first part, so I'm not going to waste your time. Sorry. So right, guys, my name is Denis, and today I came to talk about production machine learning and things that can go wrong there and what to avoid. So I just arrived at Trento. I didn't get a chance to meet any people yet. So first I'd like to get to know a bit of the audience. Who from here are data scientists? All right, quite a lot, cool. Engineers, ML engineers, data engineers. Wow, all right, I see some people roles merge. Business or product people? Anyone? All right, cool, there are some. And researchers, academia, quite a lot as well. All right, I hope that I'll have something useful for everybody. And well, maybe we can just use a USB flash stick and somebody else's laptop. Doesn't work. Right. Then I'm going to start. So first of all, I'll talk briefly about myself. I'm an engineer by background. I've done software engineering, 100 million users company. I've been working on artillery, fire control system. And a couple years ago, I moved to Estonia to study machine learning in production, to study software engineering for data science. And well, I came to share some things I've learned by doing freelance projects and working with startups who struggle with their first models to production. And there are several patterns and several things that it does wrong at the first time. So, and I'm not sure, well, cool, yeah, that would be great. Do you have a flash stick? So let's see how we can fix that. It results in a lot of technical debt, which means it's going to be hard to create a new model, update a new model, and make new features available and use new things from data pipeline. So that was a brief introduction. And I wanted to talk about deadly sins. And it was fancy to say 7 deadly sins, but I decided that it's going to be too much. And I want you to remember something. And I'm going to start with my favorite deadly sin, number 1. Writing your own serving layer. It's my favorite because I've done it myself several times. And every time, great, thank you. Wow. So, if you Google up machine learning, what? All right, I'm gonna have to keep it one hand here, one hand here. So, if you Google up machine learning in production, you're gonna definitely, oh, thank you. So, you're definitely gonna end up on some Medium article with tutorial how you can call your train machine learning model, load it from the disk into the Flask web app, and how you can serve it. And if you're really lucky, they're gonna tell you something about load balancer. And it does work. It's a good thing for a prototype, but it's definitely not gonna be good for production. Because if you remember the 4 boxes before, you'll definitely need some monitoring, some way to update models and run A/B tests and have many things deployed simultaneously. So I've done these things before. I've seen a lot of people build this thing because they don't have the better alternative. So what are possible alternatives? Well, if I were from Microsoft or Google or whatever, AWS, I would say use platform as a service. We got everything you need. And you pay as you go, just pay per request, and everything is going to be fine. You got to get monitoring and debugging everything you want. Well, I've tried it. It works fine if you really want to make a prototype and show something to the client. I think it's the best way to do that without coding. If you're a data scientist especially, you don't want to deal that much with, well, actually managing servers, running Kubernetes cluster or something like that. That is one of the best things you can do. But if you work for a company, an organization, and you need some reasonable scale and reasonable cost, definitely you want to go with something else. And yeah, I think, yeah, and yes, end-to-end machine learning platforms. If you're a bigger company and you don't have cool engineers, which is not the best place to be, but it happens, you can use end-to-end machine learning platforms. And you can name a few like DataRobot, Valahai, or H2O, and a lot of things that promise you everything, promise you whole data pipeline, inference, training, and it actually is worth its money depending on your scale. If you're a small startup or research organization, the cost might be prohibitively high for you, but, well, you have to do something. So I would say that for most of the teams, for the medium-sized companies or startups or small organization, doing some hybrid approach is the best one. There are so many tools out there, not as many as I wanted to, but for model server, there are some things you can definitely use. And I want just to mention a few of them. Well, first of all is TensorFlow serving. And although it has the name TensorFlow, you don't have to have TensorFlow model to use it. They support everything that can be called a servable, and depending on your framework and maybe if you're doing custom machine learning model, it may be easier or harder for you to implement it. But the backend, and also the backend is connected via RPC, not REST API, which is something that most people want, although I've read that they are adding support for REST APIs as well. This could be a really good thing if you want to have performant backend and don't worry about serving. And don't worry about having multiple models using the same GPU and how you're gonna do the batching and how you're gonna saturate the throughput, for example, of your GPU. So depending on the models you are using, it could be a good option. And really thing I really like is a Clipper developed by Berkeley, which is a serving platform which largely inspired a lot of things of TensorFlow serving. It may be or may not be the best things for production, but at least if you take a look at their paper, you will see the ideas behind that, which if you do implement your own model, you'll be able to do well, to do better. And yeah, so compare this to your ad hoc Flask app. They have model selection layer. It is a smart way to select the best models that using bandit methods, exploration, exploitation, and it's all built in. They have smart caching and adaptive batching, which means that depending on the latency constraints of your application, it will send requests in batches to meet this latency constraint, but also to get as much throughput as possible, so you can saturate your servers and use them more efficiently. And this is something that good engineers spend a lot of time doing, and if you can afford not doing so, you'd better delegate it to somebody like that. And yeah, sure, yeah, next. And well, so this is like key takeaway. If there was just one thing you want to remember from this talk, is that try not to implement model server by yourself. Use something like TensorFlow serving, Clipper, or well, Kubeflow, or Seldon Core. Some things out there that have done it, that engineers have worked on that for a while. And scene number 2, which is more for the teams. It's not responsibility of data scientists or engineers, but if you're both the same person, you want to care about training servants queue, which means that if your data scientist is writing code in R or Python and engineers are implemented in Java or Scala or whatever they use, you might end up at a point where somebody edited some feature and this wasn't reflected in serving. So your model in being trained on one feature set and trying to serve another feature set, and this leads to a lot of silent failures. And TensorFlow and Google, of course, they do have a thing called TensorFlow Transform, which is open source for quite some time already, which allows you to have the same computation graph for both training and serving, which is quite nice and runs a lot of devices. It feels like I'm promoting TensorFlow, but I'm not. I don't like it personally, but they do a lot of good things for production. And well, so you can use TensorFlow Transform, or you can version pipeline, and ideally you'd better to have the same code running in training and serving, and you can use Lambda architecture, for example, for that. But this might require more technical engineering, like using Spark, Flink, streaming services, and things like that. Well, and number 3, there are a lot of data scientists here. I'm sorry, guys. The thing that you ought to do is to validate the data in training and in serving. You definitely have some assumptions for every feature you have. You can assume that user age is between 0 and 150. You can assume that the salary is in this range, or the weight of a person in this range, and a lot of other things. You can take a look at TensorFlow Extended. I'm sorry for saying TensorFlow again. Maybe it sounds like a curse word here. Everybody's for PyTorch. But if you just take a look how they approach it, enforcing the expectation of the data from the human expert, and then from the data. When you have training data set, you can basically extract things like the distribution, the mean, the standard deviation, and then later in serving, over some time window, you might see that your data in real life is different from what used to be. Or you have categorical variable, and like on this example, that's something they have. Just take a look. Really, I cannot explain it. I wasted so much of your time. This is definitely worth of your time just to see how they approach this problem with their thousands of models. So you have a schema for a feature, and you want to have everything in your training data set to conform to this schema. And if it doesn't conform, either update the schema or fix the data. And also it has some neat things which are expensive to implement, like smart suggestion how to update the schema, but just remember to have at least some checks on the data and have something like unit tests for the data itself in training and serving. And I'd like to finish, I have just a few times, so I'd like to finish on a note. Do machine learning like a great engineer you are, even if you're not an engineer, and not like a great machine learning expert that you are not. Of course, you can be both of them. So just try to approach the data science projects less like experiment and let's try things, but also when you want to go to production, try to think how you can make this thing reliable, and that is going to last for not 1 month, but for years, and somebody who will come after you will be able to work on that and approach it. And few things I really want you to do if you have models in production right now. Actually, how many of you have models running in production? All right, so quite a few. Others will have at some point soon. So look at these 3 papers. They are quite simple. They're not super technical, but they give great mindset. Rules of Machine Learning by Zienkiewicz. It's quite lengthy page, but it has so many ideas being built up by experience of building Play Market services, AdClick, auction for Google, and things like that. The Machine Learning Test Score. Just take a look at this paper and see how your project scores along that. Oh, and yeah, sorry. And check out the model servers and tools. Well, don't be tempted to write a simple Flask app if there is something in which you can spend 10 hours on integration and it will work better for years. And I'd be glad to hear about your stories of putting machine learning in production. And well, let's connect, chat, and it will be super interesting for me to have a talk. And next, please. And next week I'm joining Taxify, which is a ride-hailing platform, and this is the fastest growing European startup. We recently got investment by Daimler, who is a car manufacturer, which brought us to unicorn status. So if you're interested in working with top tech talent in machine learning and data science, be sure to check out our career page. We are hiring across several locations in Europe. And well, maybe there is something in it for you. Thank you very much, and enjoy the rest of the conference. And do I have some time for questions? Or probably we are running out of time, but if there is something super urgent, then they can ask me, otherwise I don't want to. Question? Yay.
I don't know if this qualifies for production, but we see an increasing interest, both from scientific point of view or for being important things, to have interaction with the users. Mm-hmm. So to collect intermediate products, so getting access to intermediate of the machine learning pipeline. So have you seen any specific environment in which you have either visual or interesting access to deep features or correction of boundary examples?
So
I'm thinking this is going to become massive. For the moment, it's just for a few doctors, but it's going to become massive.
Excuse me, do I understand your question correctly? That are you asking about whether are there tools to look at the internals of machine learning model or
No,
something
no, no.
else? Sorry.
I'm just saying within the same framework to have a very powerful, let's say, distributed system for production. You have seen this stuff being used in strong interaction with the users, so they can provide the feedback, alterate results, indicate, add annotation as needed.
So are you talking about providing feedback for the...
We can talk later.
Okay, yeah, sure. Would be great. All right. Then...
Okay, thank you.
Yeah. Thanks so much.
It's okay. Can you hear me? Okay. Thank you for coming, and sorry for the delay. I'm going to show you this presentation, illegally shorter than the title. It's about implementation of KPIs, these key performance indicators. And we are a company based here in Trento. And our core business is assisting our customers that are managers of wastewater treatment plants. And so, first of all, simple question: who are the biggest masters in the business of the data? And in the galaxy of social media. But in the real world, we have many other subjects interested in data, and also especially in last decades, we have seen that data are really important for many type of industries, or for health data are really important in the big data projects and banks and so on. And we are, in fact, in one of this kind of industry using data. So we collect data first from a field. We have sensor probes and PCs on the plants, and we transmit data on our servers and our PC, and we use some definition, some function written in Python to achieve data in a more comfortable standard, so that will be used in a more comfortable way to analyze data. And also we have to we use classes for raw data and also for processed data that are output of the scripts we wrote in Python. And here are some examples of how we do this. It's quite simple, but the interesting is that we have for every class different kind of pre-processing methods defined just to improve the quality of data. And in fact, we know it's really important to have clean data, to have a nice data set to analyze. And so we have to replace not a number or spikes or feel missing data. And so there are also examples on how we do this. And also here there are many scripts, quite simple, but behind in all the code there are many variables we consider. And of course we use most common packages as pandas, NumPy, math to do this. But we are facing with many megabytes of data and collected every minute and replicated from many plants. So we of course have to consider using databases, and our choice was to use MongoDB with PyMongo as main packages used. And also the architecture we use for database, it's such a split architecture. We use three collection, three part of database. One with raw data, that is, there are exactly the data, the time series obtained from the field. And another collection we use is with instantaneous data. So there are the same data but pre-processed, and also with some reshaping. And we have daily data, and there are obtained with using some statistical calculations, and also there we put the output of the KPI calculations. And so this KPI, in Wikipedia you can find the definition, and it's a type of performance measurement, and evaluate the success of an organization or of a particular activity in which it engages. So I think in an age where the success seems to be the most important thing to achieve, it's really important to have some indicator of the success of an organization. And normally we think about data analysis as something for most of people in the world is to get some graphs or colored graphs, but we have to put more to give a plus to our customers. And so from this first analysis we have to add some more to have really useful data for our customer that have to take decision. So we have to help them to take decision, and we could do this with some more calculation. These are this is a list of some KPIs we are defined in our work, and the ISG is the main indicator we have defined, and it's an indicator of the general behavior of the plant, and can give us an information on if a plant is working in the correct operating range. And the ISO is an index of the operative stability, and give us information about the load state, if a plant is underloaded or overloaded, and so we can set up parameters to optimize the working of the plant. And the IQ is indicator referring also to the consumption in cubic meter of the treated wastewater, and it also talks about low and high low of the plant. And IC it's means a specific consumption. So it's derived from the correlation between the ammonia, nitrogen, and ammonia concentration. Don't worry about these biological terms, but it's really specific. And it points out a probable malfunction of the ammonia probe. So it's really important for our business, because when we have a problem with ammonia probe and when it's broken, we maybe have to wait many days before replace it, and so the plant could not working properly. And so to have an indicator that give us information about the state of the ammonia probe is really important. And also our R&D group, we are working to use also machine learning algorithm to get this information before it occurs. And the IE, it's an energy indicator, measures how much energy is wasted. So it's really important to not waste energy and oxygen than necessary. And so these are some other example of the definition class definition we wrote in Python. And here is, sorry, it's blue, it's not so readable, but ISG, and so it's one of the indicators seen before, and there's and other examples. But finally, what we have to do is to visualize, to have a nice visualization for our customer mainly, also for us, but mainly for our customer, because the background of our customers is not informatics, so they love to view this kind of visualization. And here is a visualization of ISG for our plant, and this is the behavior, and these almost horizontal lines are percentile that we calculate to see if the range, the operating range of the plant it's okay. So another plus we can give to our customer is a decision tree. Decision tree, as you've seen in the part of code I show you. It's really simple to implement. It's a series of if-then-else cycles. I'm not referring to complicated decision tree algorithm, but it's really important for us and for our customer because can help us to know what's the cause of a problem that we have seen in a plan. So analyzing all the possible causes, and here every node in fact is evaluation of the indicators I've shown before. So we have all the analysis and to get finally the most probable cause of the problem occurred. And this is a typical visualization we give to our customers. In this case, it's a dashboard, it's a web-based dashboard provided by our partner. And so in the horizontal line we have days, and in the columns we have the text message that are output of the decision tree. So it's really easy to see for customers. So as conclusion, I can say that Python really helps and eases KPI implementation with all the tools. And KPIs and decision tree are really a good help for customers, as we've seen. But dashboard mainly have to be well designed, and well designed. I mean, we have to be able to think with the brain of our customer, not only with our brain, because they have different needs, different backgrounds. And also a good communication is essential for valuing our work. And so, in fact, in conclusion, Python is really appreciated in industry, and not only in research field, but also in industry. And so we are also hiring today. Everybody is hiring. So if you're hiring, if you are interested, and we are in Trento. So if you are enjoyed Trento, it's a good choice. And so if you want to contact me, there are contacts here. Thank you.
How did you find your tree? I mean, you wrote it down, but somehow you must have come to this tree.
Here?
Yeah.
This is a really simple algorithm, because we are starting with an event, an unwanted event, and then we consider the value of ISG. So if the value of ISG is below a threshold, so we move in one of two choices. And then we consider other indicators values. So it's a series of evaluation of indicator values. And so it's this kind of decision tree. Maybe a decision tree, we are thinking about complicated algorithm, but in this case it's really simple decision tree algorithm.
Okay, thank you. Sorry for the delays and the problems we had with video output. Hopefully you enjoyed the talks. Let's have some break.
Ok, adesso qual è vostro? Sì. Perfetto.
studio ho avuto tipo che se sapevamo, cioè aveva già provato, aveva avuto comunque problemi.